Yeah, baby, are you ready?
Yeah, okay. Can I start your screen now?
Mm-hmm. Dave, do you need to give her permission or?
Oh, I don't think so. Maybe. I don't think so. I think she could just go. Yeah.
Yeah, I think it works. Yeah.
Okay, so it's our pleasure to have Beibei Liu from Georgia Tech, and she's going to tell us about triple linking number and Heegaard Floer homology. Thank you.
Thank you for our current invitation. It's great chance. It's a great chance for me to look at of you again and see you again. Yeah, it's a great pleasure to give a talk at Georgia, University of Georgia, though it'll be more pleasant to give in a person, but yeah, that'll be fine. So I'm going to talk about triple linking number and the Heegaard Floer homology. This is a joint work with Eugene Gorski, Ted Liedman, and Alison Moon. I'll start the lecture with this very famous theorem by Licorice and Wallace. That every closed oriented connected three manifold M is obtained by integral surgeries on links in S3. So that seems like a good way to see three manifold is actually seeing the surgery from the integral surgeries on links. So on the other hand side, we say like if we get a surgery, maybe we can also say some restriction on the link, which links we do the surgery to get the three manifold. For example, if we have some surgeries over the knot K, which give you the S3, where K is an integer because we're talking about integral surgeries, then actually we can conclude like K is the knot. And you can also furthermore say the framing must be plus or minus one. This framing just can be obtained from the homological condition. And this link detection might involve something about, from my side, from my view, a point if you want to see like this knot detection can be seen from the Heegaard Floer homology. But there may be other ways to see this knot detection from different experts' perspective. Another example is like, if you just do one integer surgery, which give you the Poincare homology sphere, then actually you can also say something about the knot. Either the knot K is the right-hand trefoil and the corresponding framing is one, or the knot K is the left-hand trefoil, which is the mirror of the right-hand trefoil, and also you get the, oops, well. So now the framing is not K, instead it's K minus one. However, if we would like to say more general, if when we increase the number of the components, it will actually, this question will become extremely hard, and it's like impossible to say anything about the link information. Even we just consider about two component link. So for example, you can ask a similar questions is like, if we have a two component link, and you do some framing along this knot, this link, and you get S3. Can we say something about the link? And can we do some link detection? And also you ask the similar problem about the Poincare homology sphere. It's kind of impossible to do some link detection, even we just consider about two component link. And also in general, if we just ask like, can we get some connection of the Poincare homology sphere for just the surgeries on two component link? Do we know whether there exists a link else such that we do this or some framing when we do the surgery, you can get the connection of the Poincare homology sphere? It is also a very hard question. If you just consider two copies of the connection of Poincare homology sphere, it's not that hard. Well, you can just find one example, which is the disjoint union of the right-hand trefoil. So this is a trivial example. But if you just increase the summand, like 3 or 4, even 100, it's not sure whether you can find such existence of the link such that you can do surgery to get the connection of Poincare homology sphere.
No, I don't understand your question. If we know that every three manifold is surgery on a link, so.
Oh, I restrict on two components.
Oh, two components, sorry, I missed that somewhere, yeah, okay.
Yeah, But you're right. In general, as long as you increase the number of the components, you can surely obtain any number of connections upon correct homology sphere. Other questions or comments? Great. So seems like it's helpless to say something when we increase the number of the components. However, if we would like to generalize the result for this not case, this is still something we can say, though it's not the optimal things because we would like to add some assumptions, but still we would like to generalize the scenario for the not case is we proved that if we have a link L, this L component, and also you assume this is a Brownian link. I'll say what it means by Brownian link in a moment, but let's just finish the statement first. So you suppose you get the surgeries 1 over M1, etc. 1 over ML of this link is some Poincare homology sphere. Then actually we can conclude like if the number of the component is 2, we actually can get a link detection, say the link is the Whitehead link, or its mirror, depends on the framing, where M1 times M2 equals to 1. And if the number of the component equals to 3, then actually we can say the link is the Brownian ring. And the framing is really just depends on the ring, and we make the absolute value equals to 1, but you would like to have all the framing with the same sign. And if you go further, if you just increase the number of the components greater than 4, then no such link exists. This is the best you can do to increase your number to be 2. However, we need to add this assumption for Brownian. So let me just say one sentence to explain what the Brownian means. Brownian means like all proper sublinks are trivial, like all proper sublink are a link. So this is a very strong restriction. However, adding the strong restriction, we can also say explicitly what your link should be. Yeah, in general, it's kind of helpless to give some link detection generalized to the not case. So instead of saying, instead of giving such not detection from the surgery, we're going to give some connections between the invariant of the link and also invariant of the 3 manifold. So in this talk, I'll concentrate on 2 invariants. One invariant coming from the link, which is called the Millner number, and the other invariant is a 3 manifold invariant, which comes from the Heegaard Floer homology. So let me briefly say something about the Millner number. The Millner number, I call it a mu. Sometimes people use mu bar and sometimes people use mu. There is a small difference between mu bar and mu, but let me just ignore the difference and let me just denote it by mu. And this Millner invariant in general is an invariant for links. It's not one invariant, instead is a set of invariants. It depends on your index. So this I is an index, write it as I1, I2, I3, I4, etc., In. It depends on the number of the components. So for each index, I1, I2, etc., from In, you can give a Millner invariant. So the Millner invariant has a length. It's not only one invariant. Instead, it's like a set of invariants. And the most common Millner invariant you have seen is actually mu1 to L, which is the linking number for 2 components. If L is a 2-component link. So the most common Millner number you have seen is mu1 to L, which is the linking number of L1 and L2. And also this common linking number helps us to distinguish this on-link and the half link. is the first one has the trivial linking number, and the second one has the linking number +1 or -1, depending on the orientation on the hop link. And in general, you can talk about more Milnor number, like you can talk about mu1212 or mu121 of this link L, and they all have their own meaning, and by just changing the index. The thing I just want to mention is like Milnor first defined a set of invariant in terms of the fundamental group of this link complement by looking at the lower central series. So it's like a huge lot of explanation to give you the explicit definition for the set of Milnor number. So I won't do that because I think it is very exhausting and it's very complicated. Instead, since this talk, I'll just concentrate on one Milnor number, which is called the triple linking number mu123 of L. So this is called the triple linking number. And this triple linking number is used to distinguish this unlink and the bromine rings. So for the unlink, you can see is just the split union of 3 components of unknot. And for the bromine rings, just modify the intersection. Okay, so for the 3 component unlink, one thing that is the triple linking number for this one is 0. And for the bromine ring, the triple linking number is +1 or -1, depends on the orientation. So for the bromine rings, you can see like every proper sublink, like the 2 component sublink, they're all unlinked. So the linking number does not tell you anything because they all have trivial linking number pairwise. However, you can still distinguish them by looking at the one step higher, the triple linking number, to distinguish these 2 links. So like I said, I won't give you the Milnor's original definition of this triple linking number. Instead, I'll give you like a geometric interpretation for the triple linking number given by Cochrane. Say if you have a 3 component link L1, L2, and L3, you assume like the pairwise linking number Li and Lj is 0. So this is called the algebraically split link. And then we pick cipher surface Fi for each component Li. So I have 3 cipher surface F1, F2, and F3, such that Fi intersect Lj is empty when I is not equals to j. And then the triple linking number mu123 of L equals to the minus of the algebraic intersection number of the 3 cipher surface F1, F2, and F3. So for example, we would like to see why the bromine rings has the triple linking number to be +1 or -1. So by using this definition given by Cochrane, you can see it's not very hard. I will just redraw the bromine rings. Okay, so this is also the bromine rings. I just drawing in a different way. However, you can see like if you throw away one component, the other 2 components are unlinked. So this is still bromine rings. And by using the definition, you would like to find 3 cipher surface for each component. So it is not just hard to see some candidates in this picture because they're all unknown components. For example, this component L1, they bounce a cipher surface, which is only a disk. However, this disk is not a very candidate surface because you need the cipher surface which have empty intersection with other 2 components. If you just choose the disk, it will have the intersection with the component L2, and this is L3. So this is not good candidates for F1. Instead, I'll just pick the red part, and then they'll glue the tube to dig out how to say that? I'll just add a tube at the intersection point of this disk. So now your new cipher surface for F1 is actually part of the disk, but then you attach these two tubes. So that by adding these two tubes, you can avoid the intersection with the component L2. And for the component L2, there is also an obvious cipher surface it bounds. And actually it's the disk it bounds here. So that you can see is also not a very good candidate because this F2 has non-empty intersection with L3. So this is not good in the definition. However, the good thing is like the yellow disk has non-empty intersection with the component L1. So you can still do the same procedure like adding a tube in the yellow disk to avoid the intersection with L3. So by using this trick, you can find the cipher surface F1, F2, and F3 satisfy this condition. And at the end, you get like, you see like your intersection of L1 and the L2, your intersection of F1 and F2 is really just this yellow closed curve here. And the intersection with the cipher surface of F3 were just one point intersects the disk bounded by L3. So just by drawing this cipher surface in the geometry interpretation, you can see like the triple linking number of the Brommer rings is +1 or -1, depends on the sign. And actually that's exactly the generalization for a linking number, right? Just recall like how you define the linking number. You need to find a cipher surface for one of the components, which is the complement for the other component. And then you see the intersection number for that component with your cipher surface. So it's exactly the generalization for linking number. And actually for all higher order Milnor number, there is such geometry interpretation given by program. But we don't need to talk more about that because we just need to concentrate on the triple linking number in our talk. So any questions?
Hi, yeah, so this uses the fact that the pairwise linking has to be 0. Is the definition just different if it's not 0?
Oh, sorry, what was the last sentence?
Is there a different definition, like similar sort of construction when the linking, pairwise linking isn't necessarily 0?
That's a very, very good question. So that's relates to the first thing I talk about is mu and mu bar. So the Milnor number is only well defined when you moduli some proper link information. For example, you see like the linking number is mu1, 2, and then the next Milnor number you would like to see is mu1, 2, 3. So people are always interested in like the first non-vanishing linking number. If your linking number is non-zero, you can still define the triple linking number. Everything is the same. However, the geometry interpretation is not very successful. You need to use the Milnor's original algebraic definition by going to the lower central series of the fundamental group. It still makes sense. It's just like it does not so good to see in the geometry way. And also, if the linking number is 0, then the triple linking number is the first non-vanishing Milnor number people are interested in.
Okay, thank you.
Thank you for a question. It's a really good question. Other comments and questions? Great. So yeah, so the invariant I would like to see in this talk for the link is the triple linking number mu1, 2, 3. And then what about the invariant I would like to see for the 3 manifold? As I mentioned before, like this invariant comes in from the package of Heegaard Floer homology. So let me maybe just quickly review this package and what kind of invariant I'm looking at. So for any 3 manifold, which is closed oriented and connected manifold M, there is a set of 3 manifold invariants introduced by Oshra and Zavo. And also they start with some chain complex CF minors of your three manifold M. And for expert, I think there are so many experts here for Heegaard Floer homology. Anyway, so there's just the so this chain complex is really some Lagrangian flow chain complex from the symmetric product of the Heegaard surface. So this is a chain complex, and the chain complex is we're regarded as a module over Fu, where U is a formal variable. And then we can take the homology of this chain complex, which we called it HF minors of M, and also it is an Fu module. And this homology group is a three manifold invariant. Though we are not looking at explicitly for this invariant, but our invariant we care in this talk will be extracted from this homology group. So the next property for this homology group, HF minors of M, comes from like it will split based on the spin C structure of your manifold M. So I write it as a direct sum of the three manifold in terms of each spin C structure. For example, if you have the three manifold is just the trivial, the simplest the three manifold S3. So there's only one spin C structure, and you can just talk about that spin C structure for your three manifold S. It's very simple. It's just generated by one element. You can just call that element X as an Fu module. And if you draw this picture, then you just have X, Ux, U square X, U cube X as a U module. In general, if your manifold is a rational homology sphere, then your homology group HF minors of M at each spin C structure looks very similar to the case of S3. Instead, it will have like one Fu part as what we have for S3, but direct sum is some U torsion. So this U torsion part sometimes it's hard to compute, but actually during the whole talk, the invariant we care is not from this U torsion part, but only from this Fu Tauber part. So we don't care about this torsion so much in our talk, which means like, in explicit, I'm trying to say like, once you have this Fu part as a Tauber, then there is a Q grading at this Tauber. For example, for the three manifold S3, I have this Fu Tauber generated by X. Once I have a grading for X, here is 0, then each time I act by this U action, it will decrease the grading by 2. So inductively, you know the grading for the whole Tauber, which is -2, -4, -6, etc. So the invariant we care in this talk is actually the grading information in the Heegaard Floer homology. We care about the grading for the generator for this Fu Tauber. And actually it's called the D invariant. So I'll give the definition. The D invariant of the three manifold M is called the DMS with some spin C structure is the grading of the generator of this Fu part in HF minors of M and S.
Do you need like a rational homology sphere? I guess, how do you know that the free part is one tower in general?
It's a very good question. So as you can see, like I add this assumption M is a rational homology sphere, then I would just say, well, my HF minors look like that. But as Melissa, but as I pointed out, I think like in general, if your manifold is not a rational homology sphere, like it has non-zero B1, then yeah, then in general, you don't know this homology, what this homology looks like, and you're not sure what is the rank. So there's ambiguity to define this D invariant. However, we know like I know there are a lot of experts here. For experts, you might also know the D top and D bottom, which we'll see that later in this talk. But at this current moment, let's just assume we're working on rational homology sphere, and we're just read our invariance D as the homological grading of the tower. Is that okay?
Yeah, sorry, I forgot. I didn't see the qualification. So yeah,
Oh, there, that's
thank you.
totally fine. No. Feel free to ask. Yeah, it's totally fine. Yeah. So far, it's good to just constrain on rational homology sphere, though in the proof, we might need to see other kind of general three manifold, but so far it's fine. Other questions or comments? Okay, so our main theorem is to relate the D invariant of the link and also the Milnor number of the link and the D invariant of the surgery three manifold. So if we have a three component link, is algebraic split, which means the linking number is 0, such that all two component sublink are L space link. If the triple linking number mu1, 2, 3 of this link is non-zero, then the D invariant of S111 surgery along this link is smaller or equals to -2. So yeah, you might feel confused about the statement because I haven't introduced you what is the L space link. So it's just yeah, but I will just say in 1 minute. And also the statement just the same, like if your three component link satisfy this condition and you also know the triple linking number is non-zero, then we actually can say a restriction for this D invariant. It is very important because after we know the D invariant is smaller or equals to -2, then we know this three manifold does not bound a rational four ball. And also we know like it is infinite order in the homology cobordism class. So actually the D invariants actually give a lot of information about the three manifold, and also it gives us information about which kind of four manifold it bounds. Yeah, as I promised, I would like to give you a quick review about what is this L space link means. So for example, if we have the sublink Li, Lj, this is a two component sublink, and we say this sublink is an L space link. If we do large surgeries along this link, you get HF minors of these large surgeries at each spin C structure is really just the one FU, and you don't have any torsion. So this is the simplest the Heegaard Floer homology you can have for each spin C structure. And you need the surgery coefficient to be sufficiently large. However, there is still some subtleties in the statement of this theorem. So as you can see, like when I talk about Heegaard Floer homology, I use the field F, which is really the field Z over 2Z. However, in the statement of this theorem, actually I'm secretly using the coefficient Q. If you are using the coefficient over Z over 2Z, then the statement will need to do a little modification. Instead of saying mu is non-zero, you're not saying mu 1, 2, 3 is odd. Then you say the D invariant is smaller or equals to -2. And this D invariant and also this L space link, they're all defined in terms of Heegaard Floer homology. So whenever I say this two component sublink is an L space link, you need to specify what kind of field you are working on. Though in general, most of the people in Heegaard Floer homology work on the field F, but basically you can work over any field you like. So when I say this statement, I actually state the sublinks are Q L space links. And this is the D invariance defined of the Heegaard Floer homology in terms over the coefficient Q. If you would like to work over Z2, you would like to over the field F, then the statement is not true. We cannot say so strong for all Milnor number. Instead, we can only say odd triple Milnor number. That's the difference. And also you can work over the other field K, arbitrary field. It really does not matter, just depends on the modification of the statement and the modification of your proof. Questions, sorry, or comments? Okay. So before I go to the proof of this theorem, I would like to give you a counterexample. So you might wondering, so you might don't like this condition, like the two component sublinks are L-space link. So what if we throw away this assumption? Is it still true, or do we have a counterexample? So I will just give you a counterexample. What if we don't have the assumption like the every proper two component sublink is an L-space link? Is it still true? So let me start with this link. So this is a two component link, L1. There's a component K and the unknotted component U. This is the unknot. And this K could be arbitrary K, depends on it. You can just choose arbitrary knot you like. So this is a two component link with the linking number to be +1 or -1, depends on the orientation. I will just give an orientation on this link such that the linking number is -1. So now I want to change this two component link to be a three component link, because in my theorem, we study three component link and we study the triple linking number. And in order to raise it up to three components, one thing or one operation low dimensional topologists usually do is do the it's doing the beam double. So I'll do the end twisted beam double for K, such that now my link will be look like this. So I have so now I have a three component link. The unknotted component is still here, and the rest of them is doing beam double for the knot K. Now I have a three component link, L1, L2. I maybe won't use L1 because I used L1 already. So this is a three component link, and you might want to compute the triple mu-knot number for the three component link. And by a theorem of Cochran, it's really just the -1 times the linking number for L1, which is 1. So this is by a result of Cochran, like how the mu-knot number will be changed when you do the beam double. So we'll do +1, +1, +1 surgeries on this new link. The triple linking number is non-zero, as we have in the statement of the theorem, and we would like to see what the D invariant for this surgery manifold is. For this example, two of these components are unknot, and actually we're doing +1 surgery, so you can just blow them down. And then after you blow down this component, it's just the add sound twist in these two strands. And after you blow down this unknotted component, it just gives you the clasp as the whitehead link. So what you get at the end is when you do +1, +1 surgeries on these two knots, you actually just get one surgeries on the whitehead double of the knot K with some twist. But now you need to change the twist because this +1 surgeries will give you some twist. So this is equivalent to do the whitehead double, twisted whitehead double for the knot K, and now you're doing +1 surgeries. The D invariant for this new manifold actually has been computed by Tenji. Is 0 or 2 if m is greater or equals to 2 tau K, and equals to -2 if m is smaller than 2 times tau K, where this is the tau invariant. But if you don't know the definition for this invariant, it's totally fine, because as long as K is sufficiently large, then we can see from this relation that the D invariant for this surgery manifold is never, so it will be 0. if the n is sufficiently large. So this will give a counterexample for our main theorem, because the triple linking number in this example is 1, but the D invariant in this example will be 0, which is not what we claim in the statement. So the assumption, this two component sublink will be an L-space link assumption will be essential in our statement, though you might replace it by other assumption, but we surely cannot throw away the assumption directly. And actually you can see, like, if you consider this component and this component, so this will give you a two component sublink, which is really just link, so it's trivial. And if you see this one and this one is also trivial. So if you see this one and this one is also trivial. The only non-trivial sublink is this Whitehead double. Oh, sorry, it's not the Whitehead double. It's the component L. It's the component I denoted by 1 and 3. This will give you a non-trivial two component sublink, which is not an L-space link. Questions? Any comments? Sorry. Great. So yeah, like I said before, one straight corollary from the main theorem is for the surgery manifold 1, 1, 1 of the link L in the theorem, it does not bound a rational homology ball. And also it has infinite order in the homology cobordism class. The reason why it does not bound a rational homology ball is simply because once you bound such ball, you need your D invariance to be 0. And that's why the D invariance can give some obstructions for the full manifold it bounds. And also, what does it mean by the homology cobordism class? We say two oriented three manifold M1 and M2, they're in the same homology cobordism class if they bounce a four-dimensional manifold such that the inclusion map induces the isomorphism on homology. So since the D invariant is a concordance invariant, if you just do the power in the homology cobordism class, the D invariant will also increase. It will never be 0. That's why it also has infinite order in this homology cobordism class. At the end, I would like to give you some sketch proof of the main result. The proof actually involves a lot of details, but I'll just give you the sketch of the proof. So the first step is we would like to use some technique to reduce every sublink to be trivial. Every two component sublink Li union Lj is trivial, which really just means it's the unlink. And why can we do so? So if you if you can find one non-trivial sublink, then it is a non-trivial L-space link. Then we're just observing what is the D invariant for S11 of these two sublink, where we see what it looks like, because you can construct a cobordism, a positive definite cobordism from S3111 of L to S311 of Lij by just adding a handle towards the third component with the framing one. So you can just construct a positive definite cobordism between this three manifold to this three manifold. And then you can just use Oshman and Szabó's D invariant comparity under the positive definite cobordism, seeing like the D invariant of the whole three manifold is smaller than the D invariant for this two component sublink. And then as long as it's a non-trivial L space link, then you can prove the right-hand side is strictly smaller or equals to -2. Though I still would like to mention there's a subtlety here is if you work over the field F2, it might be not very hard because you can use the large surgery formula. But if you're working over the general field Q, then you need to do some extra work by just constructing a cobordism between S31 of not K to S3N of K, where N is very large. So for this two manifold, we need to construct a four manifold whose boundary is one surgery of not K and large surgeries of this not K. And also we would like our cobordism is a positive definite cobordism. There is a very standard way to do this is trying to use some CB2. So you can just, so it's easy to get a cobordism from S3 to S1 over K. You just attach a handle to the not K with framing 1. But in order to get the framing of sufficient large N, you can just connect some with a lot of CP2 bar, or CP2, sorry. And then each CP2 comes from 1+1 surgeries for an on-not, and then you can do the handle slice for the on-not to the not K, and you can increase the framing of this not K such that the framing will be sufficiently large. That's just a very rough sketch, but you can just construct such cobordism, and once you have this positive definite cobordism, you can see the D invariant inequality, which will give you the right answer. However, by doing all this procedure, what I'm trying to say is like you can assume all the proper to component sublink Lij, they're trivial. And what does that mean when you assume each proper sublink Lij is trivial? That means your link L is a Brownian link. And that's a very strong restriction. So now we can assume our L is a Brownian link. Is there far away to see how to get the relation between the triple linking number and the D invariant of S3111 of the surgery? So the key ingredient in the second step is using this surgery exact triangle. That we have HF plus S300 infinity of your link L with some spin C structure. And then we have F1. We do another surgery S3000 of L with some links, some spin C structure. Sorry, I haven't introduced the notation for HF infinity, but you can simply regard it as HF minus. There's nothing different. It just comes from the homology of the chain complex CF infinity, and it's just by inverting the variable U by U inverse. So for simplicity, if you don't like this notation, you can just ignore it and regard it as HF minus. It does not harm. So the surgery now I would like to see is 00 infinity, 0, 0, 0, and also 0, 0, n. For all these surgeries, you don't see how it relates to the 111 surgery. It's still a little far away from our goal. However, the good thing is like for the first thing, 0, 0 infinity surgeries. I just would like to ask anyone knows what this three manifold is?
To the 3 torus?
No, it's 0, 0 infinity. This is really just a two, sorry.
No, I was just gonna say the infinity means you ignore that component.
Yeah, that's right. So you just ignore that, and our link is a Brownian link. So you just do 0, 0 surgery on link. This just two copies of S1 cross S2. So you know explicitly for the first one, And for the third one, it's not that clear because we do 0-0 surgery for the first two components, but you do large surgery for the third component. It's not very clear what it looks like. However, the good thing is like this will relate to the D invariant of S311 of 111 of L. So this is the final thing we would like to see, and this is related to this one. And for the third candidate, 0-0-0 surgeries, sure, we don't know what it looks like because the link is very mysterious. We don't know whether it's unlinked. So we don't have any information for the third one. However, we know the rank equals to 6 if the triple Milnor number is non-zero. Then that goes back to Melissa's question. Like we know, like for rational homology sphere, HF minus or HF infinity of this manifold M spin C structure is really just one tower. Fu with well, if you just use infinity, you just have one Fu U inverse. So this is really rank 1. But now this 0-0-0 surgery along a 3-component link definitely is not a rational homology sphere. It is a 3 manifold with the first Betting number equals to 3. B1M equals to 3. So it does not need to have one tower. In general, it depends on your B1M. For general M, the most towers you can have is 2 to the power of B1M. So if your B1M equals to 3, you're expecting there are 8 towers. However, I claim like if the Milnor number is non-zero, there are only 6 towers. So here is where we use the condition the triple linking number is non-zero. So that uses the subtlety for the field you're working on. If you're working on Z2, you're fine, and you just can stay in the area of Heegaard Floer homology to find the rank is 6. That's totally okay because we have the large surgery formula and it tells you everything. But this is only work for the field Z for the field F. If you would like to work over the field Q, then though the low dimensional topology experts in Heegaard Floer homology believe like the surgery formula still holds for the coefficient Q, but it has not been worked out. So if you would really to work over the field Q, it's not enough to use Heegaard Floer homology. Then in this case, I guess like people outside of Heegaard Floer homology should like maybe know this, like now we would like to use some we would like to use some monotone flow homology and use the big theorem like the multiple flow homology is isomorphic to the Heegaard Floer homology. And that's where we use this triple Milnor number and the rank. However, the rank is really needs to take advantage of this big machinery of this big theorem isomorphic to each other when you work over the field Q. Yeah, sorry. So in just one sentence, now we have DS3111 of L in a trivial spin C structure, and we just relates to S300N of this link L in the trivial spin C structure. Minus there's some gradient shift, the length space of N1 is the trivial spin C structure. And by this exact triangle, it is smaller or equals to the D top of S300 infinity of L and S0. And we know what this manifold is. It's just the connection of S1 cross S2. So you know the D invariant explicitly, which is really just the -1. That's how we get the D invariant of your 111 surgery is smaller or equals to -2. I should mention I'm very sloppy here because as we said, for these 3 manifold, it's also not a rational homology sphere. So you at most have 2 to the power of B1M towers, which will give you 4 towers. So when I say this D invariant, it's really sloppy to write just the D invariant because you need to specify which tower you're working on, which grading information you're looking at. However, I don't think anyone here would care about which tower I'm looking at. So I'll just sloppy here write as D. And this is like the sketch of the main theorem. Yeah, and that's basically all I would like to share with you. And that's great. It's like 15 minutes talk. Thank you so much.
Let's thank Beibei. Any questions?
Well, sort of a vague question, but I don't know how much farther can you push it? I guess. I don't know how to.
Sorry, can you say it again?
My question is just how much, can you get, do you think the same tools can get you much farther?
Oh,
Other
yeah.
Miller invariants.
Can do. Yes, there's a lot of things you can think about. So, I mean, a very trivial questions you might ask is like, now we can see the linking number in Heegaard Floer homology. It seems we can also see the triple linking number. Like, can we see all the Mjolnir number in the link flow homology? One way to see it is from Alexander polynomial, but that's not good enough. Another way to see is like the Mjolnir number involving the link information is related to the cipher surface or the geometric structure of the link. So now you're thinking like, well, now I'm doing my 3 manifold and I cut them along my cipher surface for this each link component. Then I get some sutured version of my Heegaard Floer homology. Then can you see more information for these triple linking numbers? And also for the very first question is which integer homology sphere you can obtain as a surgery for 2-component link. This is also unknown, but actually I prove like if you would like to get several copies of the Poincare homology sphere, your link L should be a boundary link, which means like all the Mjolnir numbers should vanish. But that's still not a good enough candidates to solve this problem. So you also would like to see boundary link can boundary link provide extra restrictions to your link flow homology? Yeah.
Thanks. Do you know if anyone has like really tried hard just to find a link, a 2-component link, giving 3 Poincare homology spheres? I mean,
we don't think it exists.
You don't think it exists, right?
Yeah, we want to prove it does not exist.
Right.
Yeah. Do you believe it exists?
I don't know. I mean, I don't. 2-component links can do amazing things.
That's right.
So I guess I don't have enough intuition to know really whether it's possible or not, but I would start by trying to make one.
Okay.
Or at least try to get just try to get something close, or I don't know. I'll try. I'll tell you. If I get one, I'll tell you.
Okay, great. Actually, can you try this one? Like do S3 y minus 1 over 3 2 copies of the Poincare homology sphere. Can you try to?
You want 2 copies, and you want a 2-component link.
2 copies of Poincare homology sphere and the
2-component link with framing 1 and -1.
And I don't mind the linking number. I will assume the linking number to be 0.
Okay, yeah, I don't promise anything, but sure, I'll play with it.
So I have a very stupid question that at the end of your proof, you use this surgery exact sequence, and it seems that the one part that I understand you use is that after you remove one of the component, then you have unlink for the other 2 components. So this is weaker than the Brownian link constraint, right? So the Brownian link constraint is saying that so any sublink is unlinked, but you seem to only use that if you remove one component, then it exists.
It's trivial. It's
It's
so
tri- yeah.
yeah, I'm trying to say if you remove one component, the two component sublink is unlinked. So you kind of know they have unknotted component, which actually will give you the whole link is a Brownian link.
Oh, okay. I see. Yeah, so we are also only.
Oh no, I think the statement of the theorem can be generalized to arbitrary number of components, and you don't need to restrict yourself to 1-1-1 surgery. You can go to any rational surgeries like 1/m1, 1/m2, 1/m3. It's just one extra step. You need to construct some cobordism between your 3-component link to your m component link. So, because the D invariant for the so many component link is always smaller or equals to the D invariant of the surgery of the sublinks. That's just because you can construct such cobordism very easily. So the statement definitely can be generalized to more number of components, but you're looking at the triple linking number for any pair of 3 components.
So, but still so what you need to know is that after you remove one component, the 0-0 surgery of the rest of the component is something that's easy to understand and the rank is small. So would that be would that be something that one can generalize in this direction?
No, I don't think you can, at least at this moment, I don't think a good way to generalize this, because you might need to find a better candidate than the triple Milnor number. And
So okay, so maybe I also missed. What is the key role of the Milnor number that play in this game?
so if you are working on the field Z2, sorry, not Z2, F. As I mentioned before, like this, you can use the tools in Heegaard Floer homology. That's enough. The triple linking number will tells you the information for some differential map in the spectral sequence for computing the surgery.
So
that's
from the
totally
linking number. From
yeah,
the triple linking.
but yeah, but this only work out in coefficient. Then if you use the Q coefficient, we use something outside of the Heegaard Floer homology area. We use the monotone flow homology, and I don't quite sure how one can generalize the triple linking number to higher linking number at this moment.
What do you mean by higher linking number?
Like you can also go to mu 1, 2, 3, 4, or if you have more number of components.
So the triple linking number is basically the messy product, right?
Yeah, that's right.
Then you have this A infinity structure that you should be able to compute. I mean, you have this higher messy product.
That's
so
right.
then you can use those. I think you have already used those, right? So you have
yeah, I use those. I think what you're trying to say is it's kind of right in like we use one grade in grading like the monopole flow homology for 0-0-0 surgery is rank 6. That's basically use the information like the triple linking number is a triple product for the homology of your manifold. And it is non-vanishing that gives you some information about the rank.
Okay.
Yeah.
Okay, thanks.
Thanks.
So if there is no other questions, let's thank Beibei again. Thank you. It's really great.
I'm stopping the recording.
Oh, okay.